Today's notes are 5.2 expected value, and this lesson is going to look very familiar to when we talked about the population mean in Unit 3. So we define that formula for population mean as the sum of all the x values divided by the total number of observations, n. And now we'll apply that to a random variable. So we have student ages example here. So consider a population of 8 students whose ages in years are those given in table 5.8. Let x denote the age of a randomly selected student. So that's key here. X denotes the age of a randomly selected student. From a relative frequency distribution of the age data in table 5.8, we get the probability distribution of the random variable x, shown here. Express the mean age of the students in terms of the probability distribution. So we'll do that using our formula above. So mu is equal to the sum of all the x values divided by n. So in this case, we have, just add them all together. We have new notation, but it's a process that we've been doing for years to calculate the average. So what I'm doing here in the next couple steps is bringing us to a new process that we can use when we're given this probability distribution to jump straight to the mean using a shortcut. So another way to write this is we have two 19s, so 19 and 19, two of them. We have 3 20s, we have 2 21s, and we have 1 27. Dividing that by 8. Haven't done anything different besides rearranging the numbers. So another way to write that would just be 19 times 2 plus 20 times 3 plus 21 times 2 plus 27 divided by 8. In other words, we could kind of break that up using this fraction here of 2/8, and then we'll use 3/8 here and 2/8 again, and then 1/8. So we could write that as 19 times 2/8 plus 20 times 3/8 plus 21 times 2/8. Right, I'm just breaking this down into individual pieces. Again, it's the same values. And plus 27 times 1/8. So what that boils down to is 19 times, right? We start to see the resemblance here. 2/8 here, 2/8 here, times the probability that x equals 19, right? Which is this right here, plus 20 times 3/8, the probability that x equals 20, plus 21 times the probability that x equals 21, and then plus 27 times the probability that x equals 27. In other words, we have the sum of all of our x values, that would be the 19, 20, 21, and 27, times each of their probabilities. And that's all defined right here. So this formula here can be applied to a probability distribution using this formula here, making it quite a bit quicker. So the mean of a discrete random variable x is denoted mu sub x. So you'll notice the variable name is written as a subscript to the population symbol here, or when no confusion will arise. So we can simply write mu. So if there's not multiple different probability or random variables going on, we can just simply use mu. Here's how it's defined. The sum of all the x values times the probability that each of those x values occurs. The terms expected value and expectation are commonly used in place of the term mean. So we'll see this term quite a bit, expected value, which is what we named the notes today. I put this symbol or this reference here as well, just because I like the way that each of these pieces is defined, and this symbol is sometimes used instead of the mu symbol. So expected value E of x is the expectation or expected value of x. And you'll notice that this is written in much the same way. Same thing, but it's written out as a description of each part. So multiply each value by its probability, and then after multiplying each value pair, add the whole lot together. So here's another example, busy tellers. We have this Prescott National Bank with 6 tellers available to serve customers. The number of tellers busy with customers at, say, 1 p.m. Varies from day to day and depends on chance. Hence, it is a random variable x. So that would be the number of tellers busy with customers at 1 p.m. Past records indicate that the probability distribution of x, as shown in the first 2 columns of Table 510, find the mean of the random variable x. In other words, find the expected value of x. So to do that here, we can just simply use our new formula. We'll use mu equals the sum of all the x values times the probability that x equals one of those given values. And so what we're doing here is multiplying each one of these. The 0.29 times 0 plus the 0.49, or sorry, the 1 times the 0.49, the 2 times the 0.078, we get 0.156, the 3 times the 0.155, we get 0.465, and so on. And then the total is given to us right here. So then 4.118, the hard work's been done for you, but just keep in mind, this is how this is done. We're multiplying each of the x values times its probability and adding those together. So the interpretation of the mean of a random variable is that in a large number of independent observations of a random variable x, the average value of those observations will approximately equal the mean mu. And then, just as always, the larger the number of observations, the closer the average tends to be to mu. So flip this over, and we'll take a look at the standard deviation of a discrete random variable. So the standard deviation of a discrete random variable x is denoted as sigma sub x, or when no confusion will arise, simply sigma. And here's how we define it. The square root of the sum of the differences of the x value minus mu squared times the probability that x equals x. The standard deviation of a discrete random variable can also be obtained by computing this formula here, where we just add up all of the squared x's, multiplying that by the probability of each of those x's, and then subtracting mu squared. So let's go ahead and work out this problem together. We have, when we multiply 0 times 0.029, we get 0. And then when we multiply x squared times that, 0.029, we also get 0. And then here when we square 0.049, we get approximately, sorry, if we square 1, we get 1. If we square 2, we get 4. If we square 3, we get 9. Square 4, we get 16. Square 5, we get 25. Square 6, we get 36. And then multiplying these together, 0.049, and then 4 times 0.078 is going to be 0.312. And then 9 times 0.155 is 1.395. 16 times 0.212 is 3.392. 25 times 0.262 is 6.55. And 36 times 0.215 is 7.740. Adding all of these up, we get 19.438. All right, so we've done that first part right here. So to find sigma, we have to calculate this 19.438 minus mu squared, and then subtract that, and then take the square root of that. So in other words, 19.438, we actually calculated mu in the previous problem, right? So we know that that's 4.118. So our final answer here is 1.6. So roughly speaking, we have on average the number of busy tellers is 1.6 from the mean of 4.118 busy tellers. So this should take you, set you up for success on your practice problems in Math Excel. As always, if you have any questions, please reach out. I'd be glad to help.